All right, so as part of the warm-up, we're going to talk about what it means to find a function, the derivative of said function, and what is the derivative, what value are we finding the derivative at, and then actually completing the derivative for that problem. So if you look at the given warm-up, then we have that the limit is equal to sine of pi h minus sine of pi all over h. And we're being asked some questions about it. We're being asked, okay, what is the function I am finding the derivative of? Well, the function that we are finding the derivative of is the f of x. So this is the limit of f of x plus h minus f of x all over h, where x equals a is the value we're finding the derivative at. So in this case, my f of x is this second part of the function. I'm finding the derivative at pi. So my a value is pi, and my f of x is that sine of x. So you're not finding the derivative of sine of pi, you're finding the derivative of sine x at pi. So you're finding the derivative of sine x at pi. And then to actually find the derivative, we have to go through and use our rules. And one of the rules we have to look at is the sine of pi plus h. So that's kind of like the sum of adding two trig functions together. So the sine of a plus b can be rewritten as a sine and a cosine function together. So we have the limit as h approaches 0. And what we're going to do is rewrite the sine of a plus b as the sine of a times the cosine of b. So it's the sine of pi times the cosine of h minus or plus, so in this case it's plus because we have a plus, the sine of h cosine b. So then this comes from the formula sine of a plus b equals sine a cosine b plus sine b cosine a minus the sine of pi all over h. We know that we can rewrite a limit so that the denominator, which is singular, is underneath each part of the limit separately. So this is really like the sine of pi cosine h over h plus sine of h cosine pi over h minus sine pi over h. And we know that the addition and multiplication are commutative. So I can rewrite this as the limit as h approaches 0 of sine pi cosine h minus sine pi all over h plus the limit as h approaches 0 of sine h over h times cosine pi. And if you recall, we have two special limit formulas. we have the limit as sine approaches x, the limit as x approaches 0 of sine x over x is always 1. So I have the limit over here as h approaches 0 of sine h over h becoming 1. Cosine pi is a constant. The limit as h approaches 0 of any constant is that constant. So this one is simply just cosine pi. And then the limit as h approaches 0 of cosine h minus 1 all over h. Well, that is also our formula. So if you think back to cosine, we can kind of factor out a GCF here. They both have sine pi. So that becomes a constant again. So we can take out our constant. And that leaves me with the cosine of h minus 1 all over h. I'm running out of room. Probably so are you. So does anybody recall what the limit as h approaches 0 of cosine h minus 1 all over h is? No, nothing. Well, let's think about like, yes. That's 1. So then you get the limit as h approaches 0 of sine pi. So that leaves me with sine pi minus cosine pi. What do I know about the sine of pi on unit circle for sine of 180? It's the y value over here at 180. Yes. So this is 1. Okay. Number 2, what function are you finding the derivative of? Where are you finding it at? And what is the derivative? So you have the limit as s approaches -2. So again, this is a alternate form of the derivative. So you're comparing this to the limit as x approaches a of f of x minus f of a all over x minus a. So it's kind of easy to say where we're finding the derivative at because it's always the a value in the denominator for this, but it's s plus 2, and our formula is x minus. So it's really kind of like saying s minus a minus 2, which means the value we're finding the derivative at is -2. The function we are finding it at is in the beginning of the alternate form. F of x is what you start with. So in this case, we're finding the derivative of s to the -2, which is the same as 1 over s squared. So we are finding the derivative of 1 over s squared. So that gives you the limit as s approaches -2 of 1 over s squared minus 1/4 all over s plus 2. And we know that if we have fractions and fractions, we have to clean them up. So this becomes 4 minus s squared over s squared times 4, because my common denominator is 4s squared, which means over on the left we need the 4, and on the right we need the s squared, all over s plus 2. And then we know that we can't have fractions and fractions, so we multiply by the reciprocal of the denominator. So that gives 4 minus s squared over 4s squared times s plus 2. And if I look at the top, that's really a difference of squares. And I could rewrite that where I take out a -1. And that gives s squared minus 4 over 4s squared times s plus 2. And then I can factor. Cancel my s plus 2's. And that leaves -1 times quantity s minus 2 over 4s squared, which gives -2 minus 2 is -4. -4 times -1 is 4. And then in your denominator, -2 squared is 4. 4 times 4 is 16. So we get 1 over 4. Good. Okay, let's go back to our PowerPoint then and pick up with one-sided derivatives. So a one-sided derivative is where our derivative only exists from one side. So a function f of x is differentiable on a closed interval if it has a derivative at every point of the interval, and if the limits from the left equal the limits from the right. So what that means is that the limit as h approaches 0 from the right, called the right-hand derivative, of f of x plus h minus f of x all over h equals or is the same or exists the limit as h approaches 0 from the left of f of x plus h minus f of x all over h, where in the case of the drawing we have here, since the interval is a to b, the b is going to be the value over here, It's on the right. So it would transform till the limit as h approaches 0, coming in from the left. And now we want to talk about f of x being f of b. And it has it on your graph, so like you don't have to change my b's and a's, but this would become an a to match the drawing in the graph as well. So the left-hand, right-hand derivatives match the interval beginning and end. So they exist at the endpoints in the right and left-hand derivatives. If you're looking at the left from b and the right from a function has a derivative at a point if and only if the function's right and left-hand derivatives are defined and equal at those points. And it will make sense once we start to look at some examples with graphs and piecewises. Okay? So for example, we have the following function. We want to show that it has a left and right-hand derivative at x equals 0, and that there is no derivative at 0. So you can have a left and right-hand derivative, but no actual derivative. So let's look at the left and the right-hand derivatives. So the limit as h approaches 0 from the left would be looking at the x squared function, because from the left you're approaching from the negative side, so that's x squared. So this would become x plus h squared minus x squared all over h. And then that becomes x squared plus 2xh plus h squared minus x squared all over h. And your x squareds cancel, you factor out an h, and you're left with 2x plus h, which means that the slope of the tangent in general is 2x. Now we are looking at x equals 0, so that means that the limit as h approaches 0 from the left, or the left-hand derivative, is equal to 2 times 0, which is 0. So the left-hand derivative is 0. But the slope is 2x. If we look at the right-hand derivative, and again, we could use the alternate form if we wanted. That'd be the limit as h approaches 0 from the right, and then it would be f of x, which is 2x, minus f of 0, which is 0, all over x minus 0. And then we see that we get the limit as h approaches 0 from the right to be 2x over x. So the x's cancel, and we see that that slope is 2. So does 0 equal 2? No. So the right-hand derivative is equal to 2. the left-hand derivative is equal to 0. If the right-hand derivative does not equal the left-hand derivative, then the derivative does not exist. If the right-hand derivative does not equal the left-hand derivative, then the derivative does not exist. It's just like continuity. If the left-hand limit doesn't equal the right-hand limit, then it is not continuous. If the left-hand limit doesn't equal the right-hand limit, it is not continuous. If the left-hand derivative does not equal the right-hand derivative, then the derivative does not exist. We're going to talk a lot in here about graphing. So we're first beginning with graphing f and f prime. In physics, you talk a lot about a function increasing or decreasing. You talk about a function speeding up and slowing down. All of that comes from the idea of the derivative and the graph. So if the derivative is positive, then your original function is increasing. If the derivative is positive, then your original function is decreasing. If your derivative is negative, then it is decreasing. Are we okay with the chart? Still copying? So, in the example, we want to take the graph of the function and create the graph of its derivative. So from point A to point B, we are told that the slope of that graph is 4. The slope at a particular point represents the instantaneous rate of change. It also represents the value of the derivative at that point. So if you think about what we've been talking about so far, if I asked you to find f prime of A, you use the limit as h approaches 0 of f of A plus h minus f of A all over h, which gave you the slope of the tangent at x equals A. So in this case, if they tell me at A, the slope is 4, what that really means is that f prime of A is equal to 4. Well, point A occurs when x is 0. So that's really like kind of saying f prime of 0 is equal to 4. So over here on this graph, if I'm graphing f prime, when x is 0, my y value is 4. Point B on this graph is kind of like f of 1. And we know that point B has a slope of 1. So that means f prime of B is equal to 1. And B is kind of between 1 and 2. So over here on this graph, it means I have a point here at 1. And this is, again, this represents A. This represents B. So C has a slope of 0. And it kind of looks like C is at 2. So that means that f prime of 2 is equal to 0. And that should make sense based on the chart we just talked about, because point C is a max on this graph, which is an extrema, and the extrema of a function always has a slope of 0 on its derivative. The extrema of a function always has a slope of 0 on the derivative. In physics, that's where velocity is equal to 0, because the direction, if the function is changing, it's where it goes from increasing to decreasing, or its position goes from forwards to backwards. So the velocity is 0 at an extrema, or you can say the derivative is 0 at an extrema. At point D, which looks to be about 3, our slope is -1. So that means over here, this is 3, -1. At E, which is 5, it also appears to be -1. At F, which is 6, the slope is 0. So that's another 0. So we can connect our points. And there's my derivative. Notice how at A, this is a beginning point that is solid. So on my graph, I don't show an arrow to the left of point A. Now over here, this graph does not have an endpoint. So I kind of drew mine in as an arrow because it wasn't signifying an end. So to summarize our points, the average rate of change of f of x with respect to x, does that match your notes or am I missing stuff? I think there's coming. You have another. No, it's coming. This is just a summary and then we're going to do your example. The average rate of change with respect to x over an interval is the slope of the secant. Oh, this is like at the end. I know what you're saying. All right, we'll come back to it. Okay. So flip your notes over one more time. I just think they're stapled. I think I put them in backwards. Because here's the example with the ball. Sorry. So suppose that a ball is dropped from the upper observation deck of the CNN tower which is 450 meters above the ground. What is the velocity of the ball at 5 seconds? So how do you go about finding the velocity of a ball? Well, since it's talking about seconds and meters, we need to take into account the gravity in meters per second and or the general position formula. So that would come from S of t equals, and position is 1/2 gt squared. So in this case, it's 1/2. Gravity is 9.8 t squared. So it's 1/2 gt squared. And then your initial starting height. So in this case, our initial position is 450 meters. So what is the velocity of the ball at 5 seconds? Well, that's kind of like saying the limit as h approaches 0 of f of x plus h. So in this case, this is 4.9. So it would be 4.95 plus h squared minus 450 minus f of 5 all over h. And if I distribute and FOIL first, then I get 4.9 times 25 plus 4.9. 5h and 5h gives 10h plus 4.9h squared minus 450 minus 4.9 times 25 again plus 450 all over h. And the reason I didn't actually get out a calculator and multiply anything is because you have 4.9 times 25 minus 4.9 times 25. So those cancel. And then you have minus 450 plus 450. So those cancel. And you are left with the limit as h approaches 0. 4.9 times 10 is 49h plus 4.9h squared all over h. So I can cancel an h. Oops, I have it on eraser. And that leaves the limit as h approaches 0 of 49 plus 4.9h, which means that the velocity at 5 seconds is 49 meters per second. And then how fast is the ball traveling when it hits the ground? So in order to determine how fast is a ball traveling when it hits the ground, well, I need to know the time that it hits the ground. So the time that it hits the ground would be when S of t is equal to 0. Because I need the position to be 0. So I'm going to solve for t. In this case, the square root of 450 over 4.9 is not a number we can reasonably calculate. So this would become a calculator problem if it wasn't from the beginning. We don't care about negative because time can't be negative. So the time at which the ball hits the ground is 9.58, and I need to get my third decimal. Which is 3. So the ball hits the ground at 9.583 seconds. So that means that now, I need to look at the limit, and we'll do the alternate form. As x approaches 9.5, of f of x, which is 4.9 t squared minus 450 minus f of 9.583. So 4.9 times 9.583 squared minus 450 gives a very, very teeny tiny number. So it becomes minus 450 over the t minus 9.583. And nicely enough, you can actually factor out that 4.9. And that's going to become t squared minus 91.839. And nicely enough, the square root of that answer is 9.583. So they cancel. And then you're left with the limit as x approaches 9.583 of 4.9 times t plus 9.583, which gives 4.9 times 9.583 plus 9.583, which gives a velocity of 93.916 meters per second. Good? Okay. We have a manufacturing company, and they are looking at bolts, and we will do this one tomorrow.